that number is artificially inflated for safety because once you find a liveness bug, it will often lead you to writing new safety properties. Right? A dead state is a state one should never enter. So once you've discovered that a state is dead, you can often write a property that characterizes the dead state. So many bugs that we found as safety violations were first learned that they were problems because we found them using a liveness property. These three, as I mentioned, were well tested beforehand, and this one I tested by hand. So, as I said, liveness violations lead to safety properties, but what I did find by hand is that I found several bugs related to the performance of code, which I couldn't find using the Mace model checker. Because the Mace model checker only cares about whether or not eventually something happens. It has no idea or care what time it happens. Any questions on the Mace model checker? Great, moving on. So talk about performance issues in distributed systems. So what happens is you have this ring of nodes and there's messages and they're flying around all over the place, right? Nodes are rebooting, messages are going everywhere, there's lookups happening in the system, and you're trying to figure out whether or not the system is performing adequately. So what do? In practice, we gather statistics at the end, right? At the end, we look at the stats. There were 1,000 lookups, 8,000 messages. The average lookup was 2 seconds, the minimum lookup was 0.8 seconds. There was a maximum lookup of 12 seconds, but really, I mean, that's probably just a network error, right? I mean, I don't have to worry about that, do I? If I do, that means I have to siphon through all of the logs and all of the nodes and figure out what it was that caused that error. Much easier to just say, the 90th percentile, which was 3 seconds, is acceptable. We'll just write off the rest of these cases. And this is what we do in practice. And if we really need the results to be perfect, we just rerun the experiment until the bad stuff doesn't happen in practice. Okay? What we'd really like to be able to do, however, right, so Fred says, look, I'm not going to bother debugging this case. It's too hard. It's good enough for me. But George says, I'd like to actually verify that every lookup was executed the way it should have been executed. Of course, I'm not going to do this by hand, so I need to use automated causal path analysis. So what we do is we characterize paths as either good or bad. So for a lookup path, remember the lookup path from before, node A forwards his lookup to node D, to node E, and back to A. This is a good path. It's a short path. It goes back to the source. On the other hand, one of the bad paths, right, so that's what the path is going to look like, A to D to E, and back to A. On the other hand, the bad path, for example, was when the routing tables were not fully initialized, and you had traversed through B, C, D, and E before you get back to A. Right, so you can actually write a property that says a lookup path should have a height of no more than 4. And thus, if there's a height 5 or 6, it will be flagged by the pip path performance validator so that you can then go back and look at that specific path, pointing you to where in the log file you should look. So how do we do this? We start with the two nodes A and B, or all the nodes. We collect their chronological event logs. First, we identify the messages that the two nodes are sending to each other, and then we break up the log based on event boundaries. Events in Mace are atomic, and so we only worry about when an event occurs. So we break it up into messages and events, and now we can use the happens before relationship to sift this log together into one sort of unified log. Having done this, we'll then split it back apart, of course, and redraw the messages. This gives us a chronological event graph, which is a very, very useful debugging technique. In fact, this is probably the most used debugging technique that Mace provides. And all of this is done automatically. You don't have to do any work to get this graph, except write the system in the first place. Now, to do path flow verification, we'll take this a step further. And we do this by taking the events which are causally related to each other. These are the ones connected by message arrows, and making the paths for them. So, and then once we've collected these paths, the causally related paths, we'll categorize them. So the first set of paths are, the initialization paths or the timer paths, which have no side effects. Then there's the join path, where node A sends a message to node B, and so forth and so on before getting back to node A. And then you have your lookup paths. Okay? So to write your expectations, you have an expectation that the first node in the path is a lookup node. There's a set of forwarding nodes, and finally a destination node, before returning back to receiving the response. So we write this expectation, and we run our implementation using this expectation, and it actually found this path. If you think about that for a second, what you're looking at is the case where the routing table was incorrect. there was a bug in the protocol causing the routing table to be incorrect, but was eventually corrected by by a spurious message that eventually arrives, and so we correct the routing table. We didn't know this was occurring until the pip tool told us that this path existed. Right? Before, we look at the performance anomaly and we say, don't worry about it. But because of this, we're able to look at the individual paths that cause us problems. So we've used pip, We've used pip to find 17 bugs in our own implementations. This is across 3 different systems: Splitstream, which is a streaming protocol; Bullet, which is a file transfer protocol; and Ransub, which is an aggregation protocol. And it's important to note that the compiler, the Mace compiler, auto-generates most of the annotations you need to insert into your code to use pip. Pip is a third-party system, which I also worked on, but you use it by instrumenting your code with the messages and the event boundaries. But the important thing is that the Mace compiler writes all of those for you. All you have to do to tell pip is you have to say, here's where a path begins. Well, that's really all you have to do. Okay? So these paths are causally related sets of events, which are marked by fine-grained execution tasks. These paths are checked independently, and they give you sort of the ability to do what I think of as sort of flexible safety properties. Right? I want to flag things that are outside my expectations so that I can look at them more closely. And they weren't necessarily bugs, but they're worth additional looking. So these are the kinds of things, and of course pip comes with a great visualization tool as well, to let you see the paths, the aggregate statistics, and so forth. So, in conclusion, and that URL is actually out of date. It's www.macesystems.org. Sorry. Understanding is the key to distributed systems building, right? We're writing systems today that are far too complicated for us to understand. We're dealing with hundreds or thousands of nodes or hundreds of thousands of nodes, sending messages at an incredible rate. And we, as humans, aren't real good at keeping all that straight. So we need tools to help us understand distributed systems. The first part of this is the programmers need to focus on the algorithms, not the rest of the tedious details. So we built the Mace programming language, which allows you to do a structured implementation and a domain-specific language that makes it easy to build your distributed systems while focusing on the algorithms. Now, of course, algorithms are still hard to get correct. So we have the Mace model checker, which helps you find errors, bugs in your algorithms, your implementations. And then finally, correctness doesn't imply good performance. So we augment these tools with a set of path verification tools and other tools that we're working on now to try to do path verification and performance testing in order to alert the programmer to any errors in performance. And with that, that's the end of the talk. Are there any questions? I must have been crystal clear. Yes?
This isn't a question, but just a comment. I'm very impressed with what you've written.
Thank you.
In all honesty.
No more errors in your code.
Yeah. So one thing to say, Mace is hard to integrate into existing systems. So if you have a large behemoth of code that you're working with, you probably won't be using Mace. But if you're building a new distributed system from the ground, definitely use Mace. Highly recommend it. I even provide support. You just send an email, mace@macesystems.org, and you'll get a response. Code's publicly available right down to every commit that I make. So, great. Hope you all get to use Mace. Thanks.